Okay, so this one is example number 5 on the force diagram worksheet. So I have this thing is moving at 5 meters per second to the right, and it has this 30 Newton force going to the left. So the question I want to know is something. What is the normal force? Is the normal? And I'm writing it that way because you'll see that that is how we write normal force. Normal force. We just simplify it down just to the normals, what you'll hear everybody say. Okay, so now just refresh. The normal force is that contact between the box or whatever the heck this is and the ground. So I can kind of do have the force of gravity pointing down towards the center of the earth, and I have a force normal pointing up perpendicular to the surface. So the force of gravity always points down towards the center of the earth, and my force normal is always perpendicular to the surface. You get why that's important. So I want to know, what is the force normal? So pause this and ask yourself, have we changed the force normal? And then come back and solve it. All right, so let's take a look. So this thing here, what's the important question? Is it flying up in the air or plummeting down towards the center of the earth? The answer to neither of those is no. So that means if I do my free body diagram, I start by making my box the dot. I look down and go, okay, so my force of gravity is sitting up flat on earth. So here's my force of gravity pointing straight down, my force normal pointing straight up. And the only thing I'm told is that I have this force here of 30 newtons. So that tells me this box is actually slowing down. I'm told that it has a velocity of 5 meters per second going to the right, but that doesn't tell me anything about a force being applied in this direction. In fact, the diagram that I was provided shows that there's only a force going that away. So if my velocity is going that away, that means this force applied that way is slowing it down. So the snapshot isn't telling you that this is going at a constant 5 meters per second, because if that were the case, I'd have to have another force going this direction that balances out that 30 newtons. So remind yourself of that. So I have these two things, but this thing here isn't at an angle. So let's take a look at the sum of my forces. And again, I'm going to define what is positive. I'm going to go with to the right and up is positive. So the sum of the forces in the x, let's see, I have this 30 newtons, negative 30 newtons, because I've defined to the left as negative. So negative 30 newtons, and there's nothing else there. So it must be accelerating. Or another way to look at this, well, I have the mass, so I could actually figure out what the acceleration is. So this divided by 10, just kind of on a side note, is, let's see, 30 divided by 10 says that my acceleration is negative 3 meters per second squared. That's just me putting in the mass, so 30 newtons divided by 10 kilograms will give me the acceleration in the x, which is this negative 3 meters per second squared. So that tells me, if I've defined this direction as positive, that my acceleration is negative, so this thing is indeed slowing down. I can also just look at it conceptually and see my forces. I have nothing going in the positive direction. Okay, but the question was, what is the normal? So has the normal changed because of this motion? And what I get a lot from students is that, well, if it's moving, its normal can't be the same. So what is true is that if it's moving, the friction force, if there were one, you're not told that there is, that 30 newtons could be it, the friction force is going to be different when something is stationary versus when something is moving. That's in detail soon. But that doesn't change what's happening in my y. So in my y direction, I still only have these two. This thing isn't at an angle, so it hasn't changed the force normal. So I only have those two. That says that I have that my force normal minus my force of gravity, well, not shooting up into the sky, not falling down, that thing equals 0. So my force normal will be my force of gravity. Now this thing asked me to define what that force normal is. So let's define for ourselves mathematically that the force of gravity is my mass times this acceleration due to gravity. That's times, not a dot product. So this says that my weight, my force of gravity, my weight, is whatever my mass is times the acceleration due to gravity, that acceleration that's going down towards the center of the Earth, right? So at the sea level, this value here, G, equals 9.8 meters per second squared. And you'll see in a lot of my examples, I'll round this up to 10 just because it's easier to work with. But I want to make one very important point here, is that what people do is you start getting in the habit of just throwing numbers in. And you look this up and you're like, well, it says it's negative 9.8. I've defined here my directions of everything. When I put in this negative sign, when I did the sum of forces and I subtracted the force of gravity, I did so because that gravity vector is pointing down. And I've said that down is negative. If I come back here now and put in a negative value for the acceleration due to gravity when I do the math here, I've given the force normal a negative sign. That suddenly means that what I've done, in effect, is taken this force normal and pointed it down. It's no longer, I've changed it from pointing up. So when things are getting more complicated, and they are this week, you're going to see that you need to be very careful with that. Don't let yourself put in negative signs after you've done this. This accounts for all of your signs. The only thing you need to know is that the acceleration due to gravity is 9.8. And we'll derive that later on in the course. There you have it.